Hi, my name is Nikos Petrelis and the paper I present is entitled Hypervisor-Based Platform for the Development and Verification of Reliable Software Applications and was carried out by the Embedded System Design and Applications Laboratory in the context of the Xandar project funded by the European Union Horizon 2020 program. In the Xandar project, a holistic model-based toolchain has been formulated that follows the X by construction paradigm. This is a stepwise refinement from specifications to executable code that results in systems with guaranteed non-functional properties. Xandar defined also metamodel extensions, a library of safety, fault tolerance, and security patterns, and investigated many further techniques for design automation, verification, and validation. In the project, the actual code generation procedure is performed by the XBC backend that efficiently performs the code optimizations, code parallelization, scheduling, mapping, and runtime system generation of the input software modules on the target platform, ensuring that the predetermined deadlines are met. This paper describes the main features of the XBC backend, including the generation of the hypervisor configuration files that are customized for the target multi-core platform. The use cases analyzed in Xandar showcased that the proposed XBC backend was able to output acceptable solutions in an efficient manner. The general architecture of the XBC backend toolchain is shown in this slide. Initially, we examine the source-to-source optimizations that accept as input the unoptimized code of the system runnables. Code optimizations can be applied either manually by the developer or automatically by the compiler or other tools, or by using a semi-automatic optimization approach where the work is split between the programmer and the compiler. In latter case, the code optimizations and their parameters are specified at a high level by the programmer, leaving the implementation tasks to the compiler, which executes the process fully automatically. To this end, several source-to-source transformation tools exist, such as Pluto, Loopy, Oreo, and other, but in this project we employed Pluto because it is easier to use and has a larger community. It is important to note that Pluto automatically checks the correctness of transformation so that incorrect transformations are not carried out. The Xandar toolchain uses Pluto tool to carry out optimizations, and therefore all the runnables should be appropriately annotated. In this slide, you can see an example of how the source-to-source optimizations are applied. On the left, you can see the input code, which is annotated with a pragma scope and pragma end scope. The code between the pragmas will be processed by Pluto. We specify in the script which optimizations to apply, and Pluto does the job. In this example, we applied parallelization and loop tiling. You can see the pragma parallel 4 that Pluto added, which will parallelize the loop just after this pragma. The loop transformation supported a register blocking, also known as unroll and jump, loop tiling, loop merge, loop distribution, loop parallelization, and vectorization. Vectorization is supported only for ICC compiler, not used in this work. For register blocking, 3 different register blocking factors are used, as well as the case where no blocking is applied. This is 4 different parameters which are specified by the user. For loop tiling, 6 different tile sizes are used here, as well as the case where no tiling is applied, 7 different parameters. Regarding loop parallelization, each loop kernel can be broken down into M. M is between 1 and the number of available cores. So it is broken down into M different threads, where cores is the number of available physical CPUs. An analytical model for loop tiling has been developed, but it has not yet been integrated in the toolchain. Regarding loop merge distribution, no fuse is this called, is enabled, so there are only 2 options here. In vectorization, there are no input parameters, and vectorization is carried out by Pluto. So in overall, 56 times the number of cores optimization sets are selected for each runnable. The optimization parameters are specified by the user. And please note that the tool is configurable and the user can change the number of parameters evaluated. The solutions that do not meet the logical execution time constraints are discarded. All the optimization sets, this is 56 times core optimization sets, are carried out by Pluto, and their source code is first generated, then compiled, and then run on the target hardware platform, so as to measure the execution time of each optimization set. For each m value, m is the number of threads, as we said earlier, only the fastest optimization set is selected, and all the others are discarded. It is important to note that we keep m optimization sets, not just one, as the number of threads used for each runnable is specified by the scheduling algorithm in the next step. This procedure is applied to all the runnables, and each runnable is associated with coarse optimization sets and coarse execution time values. PolyBenchSuit was selected as the evaluation framework. Specifically, various application domains were exploited, like linear algebra, computations, image processing, physics, simulation, dynamic programming, statistics, etc. We concentrated in the linear algebra using 19 kernels in total, with mixed characteristics concerning memory and computational intensive, and how computational intensive they are. And all the benchmarks were compiled with the large dataset. The specifications of the hardware platform used are shown in this slide. This figure shows the evaluation results for the 3mm benchmark. As can be observed in this figure, the code optimizations really affect the execution time of the binaries, and different optimization sets give very diverse execution time values. Here, the best execution time value for each thread is shown. The 3mm benchmark behaves better as the number of threads increased. This is because this benchmark is data parallel. The next module we examine is the runnable scheduler. The runnable scheduler should map the runnables on the processors and order their execution so that task precedence requirements are satisfied and the minimum schedule length is obtained. It is important to note that the scheduler runs not once but many times, since first of all it needs to be applied to all the software components, and b, it is applied for each hardware configuration. There are 4 solutions on a quad CPU, 1 for 1 thread, 2 threads, etc. Since A, this scheduling problem has proved to be NP complete, B, the scheduler runs many times, it is not feasible to use time-consuming stochastic search algorithms, therefore we need to use a low complexity heuristic in this case. Such an example is Heft, which is used in this project and is one of the most efficient list scheduling heuristics in terms of make-span and robustness. In this project, we have developed a method to improve both the scheduling times, the time, which is the time obtaining the output schedule. We will not discuss this here because of time limits. And scheduling length of Heft algorithm. The scheduling length is reduced by extending Heft to support multi-thread runnables. The input of the algorithm is each software component, which is formulated as a directed acyclic graph, DAG in short. The output is the number of threads that each runnable uses and the order that the runnables are executed. The Jantar mapper generates the output schedule, but it does not provide the entire output source code because this step is not automated. Therefore, the user needs to appropriately annotate the source code. To improve the scheduling length of Heft, we propose low complexity heuristics to find which tasks are going to be implemented as single threads implementations, which as multiple thread implementations, as well as the number of threads used. In empty multiple threads, implementations, fewer processing elements are available, but with higher computation capability. In single-thread implementations, more processing elements are available, but with low computation capability. Using single-thread implementations is more efficient for some DAGs, while multi-thread implementations is more efficient for others. The default heft algorithm does not support multi-thread tasks. Therefore, to better evaluate and compare our method, we have implemented heft using either single-thread CPU implementations, this is called sheft, or max-threaded CPU implementations, only called mheft. In this figure, we show the scheduling length make span of these three methods for 81 different DAGs. As it can be observed, in the first 27 DAGs, mheft performs better than sheft, while sheft performs better than mheft for the remaining DAGs. Our method is either more efficient than both sheft and mheft, or follows the trend of the best of the two. The results are illustrated by using box plots in MATLAB. On each box, the central line indicates the median value, the displayed value shows the mean, and the bottom and top edges of the box indicate the 25th and the 75th percenticles, respectively. The three methods are evaluated using 960 random DAGs and 8 CPU cores. sheft achieves better performance than mheft in most cases, but this depends on the shape of the DAG and the number of cores used. The proposed method achieved significant make-span gains. Note that compared to sheft, the proposed method's smallest gain values are higher than the one in most cases. Now we will example the software component EDF scheduler and the hypervisor file generator. The heft scheduler described earlier was responsible for scheduling the runnables within the software components based on the number of processors employed and the cache configuration selected. In this way, alternative implementations are provided for each software component based on these parameters. Software component scheduling has to be performed according to system specifications, such as the deadlines that have to be met. This level of scheduling depends heavily on the system resources and the selected software component implementation, among the ones provided by the heft scheduler for each software component. To schedule the software components, the popular earliest deadline first, EDF in short, concept is extended to support additional features. The classic EDF algorithm is optimal provided the system has a single core processor and task preemption is allowed. However, in the Zandar project, first of all, the hardware target platform consists of multiple multi-core processor. B, the preemption of software components is not allowed in order to avoid task switching overhead. And C, the selection of the appropriate implementation for each software component has also to be tackled efficiently at the input of the software component scheduler. Moreover, as we will see in the next slide, hypervisor partition sharing has to be supported by different software components that have to run on the same CPU. This is called CPU affinity. The input of the software component EDF scheduler is a DAG graph describing the dependencies between the software components, the release time and deadline of each software component, the implementation features of the selected software component implementation. This is the number of CPUs that are required and the achieved execution time. Then, as already mentioned in the previous slide, partition sharing information has to be given. A software component consisting of tasks with different deadlines can be expressed as multiple software components sharing the same partition. Here, the details of the software component EDF scheduler are presented, but we will not give details now. But we can say that the algorithm determines the next time segmentation by the shortest of the software components that can be scheduled immediately according to the release times. The restricted and their dependencies, of course. The restricted number of CPUs may not allow all the software components to be executed immediately, and some of them have to be stored in queues waiting to be executed in next time segments. Moreover, CPU affinity has also to be taken into consideration when assigning software components to CPUs. The scheduler output of the example diagram of the previous slide is shown here for 2 CPUs. Another example is shown here concerning an aviation use case. The diagram consists of 10 nodes. You can see the results of the software component EDF scheduling using both the slowest implementations as well as the fastest ones of each software component. In both cases, 8 processor codes were available. The realization of the EDF-based software component scheduling on real hardware is performed with the aid of the Fentis XNG hypervisor. Scheduling parameters including starting, ending, execution times of the software components, number of CPUs used per software component, etc. are taken into consideration in order to schedule the software components on the right hardware resources and time slots. Based on these parameters, all the necessary C-skeleton files and XML configuration files needed are generated and compiled. The resulting image files can be downloaded to the Z-board target board, but Fentis is working on the extension to ZincMP ultra-scale platforms that offer more processing cores. Concluding, we can say that Xandar project goal was to deliver a model-based tool chain following the XBAC construction paradigm, targeting to reduce both cost and errors in the design of safety-critical systems. XBC backend of Xandar is responsible for performing the scheduling and mapping activities of the runnable and software components, the code optimization and code parallelization techniques, as well as the generation of the hypervisor configuration files that are customized for the target multi-core platform. The developed XBC backend was shown capable of addressing the requirements posed by the use case of the project. Thank you very much for your time.